Hello again, Mr. Martella back with part 2 of earthquakes. Let's review a little bit of what we talked about in the first video, and we will move on today and learn a little bit about earthquake energy, seismic waves, the different types, and how they move and the damage that they can do. So let's start with a little bit of review from the last video. Something that I touched on quickly, but it is really important if you want to understand earthquakes. Or for our purposes here in 8th grade, we study 3 different types of faults. Remember, a fault is simply a break or a crack in a large block of rock. So we have strike slip faults, we have normal faults, and we have reverse faults. And you can see at the bottom of the screen the motion of each of the blocks of rock at each one of these faults. Okay, so at a strike slip fault, you have blocks of rock sliding or grinding past each other. All right, and so the motion there is in a series of earthquakes. You see right here how the land is moving. Okay, and you also see in this GIF the whole stream changes course. Okay, as the land moves from the earthquake. We also have normal faults. Now, normal faulting is caused because earthquakes at normal faults, I should say, are caused because of forces that are pulling the rock apart. So in the normal faulting process, what we normally see is one block of rock dropping down the fault plane relative to another block. Okay, and that's normal faulting. And then lastly, we have reverse faulting. These earthquakes are caused by stresses that are pushing rock together. So in these scenarios, you have one block of rock moving up relative to the fault plane. Major destructive earthquakes can be produced at all 3 of these boundaries. Okay? After that, in the last video, we went over a few vocabulary words, and I realized the most important one wasn't defined in there at all. So I added that in there for us today. And so we can see here, earthquake. An earthquake is defined as the shaking of the ground caused by the sudden movement of large blocks of rock along a fault. Okay, so that is how we define earthquakes. Seismic waves we talked about are the vibrations caused by earthquakes. Essentially, they're how energy is released from earthquakes. The focus of the earthquake is the actual point underground where the earthquake begins, where the rock that has built up all the stress actually breaks. The epicenter is a term that you hear more often regarding earthquakes, and it is the point at the surface. All right, so the epicenter will probably correspond with the name of the earthquake, being that we name earthquakes according to the town that they're closest to. The epicenter is usually listed that way also. Okay, and a good way to tell the difference between the epicenter and the focus is going to be reported as a depth. Okay, it's going to be so many miles or kilometers deep. Whereas the epicenter is, as I said, a city or a town. It will be the point at the surface. It could be longitude, latitude also. Finally, a seismograph. That's the actual instrument we use to record ground movements during an earthquake. And a seismograph will produce a recording called a seismogram, just like in the old days when they used to use telegraphs that produced telegrams. Seismographs produce seismograms. Okay? We took a little bit of more of an in-depth look at epicenters and foci or the focus of the earthquake. And remember, we said that if two earthquakes are the same magnitude in the same area, but one is shallower than the other, then it's the shallower quake that is going to do more damage, because that energy does not have to move through as much material to get to the surface as a deeper earthquake does. We talked a little bit about how seismic waves carry energy from place to place, and in today's video we're going to get a lot more of this, a lot more detail about how energy moves through a material. The last thing that we looked at was the way that these seismic waves can bounce, reflect, or bend as they pass through the earth. And they do pass all the way through the earth directly. The 98 earthquake in Pymatuning, that thing actually was recorded on seismometers in Mongolia on the other side of the earth. Now they wouldn't have felt it, all right, but seismographs are delicate instruments, and they could definitely pick up ground movements that were started all the way on the other side of the planet. Okay? So we know that some of these waves only travel through solids, others only travel through fluids. So what's the deal? What are seismic waves? Or if there was an earthquake, what would you experience? Well, we're going to start at the beginning, right? The first waves that come from an earthquake that will reach a given area are called the P waves, or the primary waves. The primary waves are the fastest. They travel the fastest of all three of the seismic waves that we're going to talk about. They travel through the crust at a speed of 3 miles per second. Okay, 3 miles per second. They move through solids and liquids or fluids, so they'll move through any material. They if you were in a building or in your home as a primary wave, as a big one pushed through, you would feel this push-pull. We call these compression waves, okay? So they're going to cause the molecules in a material to press together, pull apart very quickly, just as you're going to see in this animation right here. So seismic wave is sort of like an accordion effect, right? You see here in the image how the waves propagate, how it squeezes the material before everything is sort of set back into its place. So primary waves, these would roll through first after an earthquake, and then there might be a period of calm. And you might think that the earthquake is over if you didn't take Mr. Martella's 8th grade science class, right? But since you did, you're going to know, look, this was just the first wave. These move fast, primary waves. By the way, 3 miles per second is equal to 10,800 miles per hour. Okay? So this compression wave that you see rolling through here, it would be moving at close to 11,000 miles per hour. Good luck getting away from it or avoiding it, right? So after the primary waves come through, as I said before, you may experience a moment of calm. You might wonder what the heck just happened. And then all of a sudden, you're going to realize that the earthquake is not over yet, because the secondary waves are about to push through. These waves travel at about half the speed of the primary waves, about 5,000 miles per hour. They're not slow. As they pass through a material, these cause the particles to be shaken. So this is what's going to give you your up and down or your side to side shaking. Okay. Primary wave comes through, boom. It's like a blast, a compression wave. A little bit of a pause. Then the secondary wave comes through. This is going to last a little bit longer. And this is where things are going to be shaken up and down, or side to side. The secondary waves will only travel through solids. They do not travel through fluids. And here's the action of the secondary wave as it passes through. Okay? So you get the up and down, or if you would turn that block over, side to side. It depends initially on how the rock broke, whether that shaking is going to be more up and down or more side to side. But we have seismographs that measure both the up and down shaking and the side to side shaking that can be caused by secondary waves. Okay? So if you were in an earthquake, you'd feel the compression of the primary waves come through very quickly, then a little bit of a pause. You might think it's not you. You took Mr. Martella's science class. You know there are secondary waves coming. So all of the shaking, it may last seconds, it may last minutes. And you might think, ooh, I made it. If you didn't take this class, right? But you did. So you know it's not over yet. And this is why earthquakes do so much damage, right? You get two sets of waves coming through, that might weaken things. Then you're going to get the surface waves moving through. Now, here's the bad news. These things move along Earth's surface. They cause the ground to roll. They cause the largest amount of ground movement and the most damage. They're the slowest moving of the waves, all right? And in large earthquake events, people have reported seeing the ground rolling, all right? Seeing the ground rolling, okay? So let's check out the motion of what they call the Rayleigh wave. This is the surface wave. I'm going to put my pointer here, and you see as this wave passes through, everything is just rolling along. These would be large, huge pieces of the Earth's surface that are doing this. In large magnitude earthquakes, you couldn't stand. Okay? So the surface waves are the slowest moving, they do the most damage, and they're the final, sort of like the icing on the cake as far as the earthquake is concerned, until you get to the aftershocks. And we'll talk about the aftershocks more coming up pretty soon here. Okay? So, seismic stations are the places on this planet where we have equipment that will monitor ground movements and will tell us if there may be an earthquake or not. So seismic stations have seismographs, which are instruments that are used to record the motion of the ground during an earthquake. Now, they're installed in the ground throughout the world. We have a seismic network. They operate as part of, I think I just said, a seismic network, and they produce seismograms. I know it's tough to see the one behind me right here on the wall. You'll see it when you come into school, though. This is an actual copy of the seismograph from the Great Alaskan Earthquake way back in 1964. Okay, that was over a 9, right? So, you know, most of them are digital now. You don't get big paper ones like this. But you know, they show up very clearly on the computer, just like you would see it on paper. All right. And I believe that I mentioned, maybe not to every class, but in our area here, Penn State Beaver has a seismic station out there at their campus, and they're constantly recording ground movements here in Western Pennsylvania. Okay. So there are two types of seismographs. There is the vertical seismograph and the horizontal seismograph. Okay. The vertical one that you see pictured on the left on the screen is going to measure up and down shaking. All right. The horizontal on the right is going to measure side to side. So let's see how they work. You're going to see very soon the earthquake start. And what I want you to watch is here, as the earthquake moves the instrument, it doesn't move the mass. The mass here and the pen never move. That's why it's attached to a spring, okay? It's the whole rest of the contraption that moves. And it moves as far as the ground moves. That's how we measure. Watch one more time as the vertical seismograph records. I'm going to put my mouse pointer right here, and you'll see this does not move if it stays. See, the mass itself does not move. The ground around it and the rest of the seismograph does. And once again, this would be the seismogram that's produced. So if we're measuring the horizontal movement of the ground, it's the same concept here. The mass, the weight is not going to move. Once the earthquake energy starts to hit, here comes your primary wave, secondary wave. And that is how we measure how far the ground moves. And that's part of the formula as to how we calculate the overall magnitude of an earthquake. Okay, I think this is a good place to stop for part 2. We will be back and we will talk more about earthquakes in part 3. Thank you all for tuning in, and we will see you in the next video.